taking the compactification to be 6 here?
Not necessarily. Think of it as a product space, just some single scale space, and for simplicity, let's consider a product. But I want to allow for different signs of the curvature, so a sphere would be an example, but not the unique example. Of course, if you compactify in a sphere, you get anti-de Sitter space. In some cases, you can add ingredients to that to upgrade it to de Sitter. So that's an interesting story. I'll say a little bit about that, but sort of qualitatively later. But yeah, at this level, a sphere would be an example. But.
So before Eva starts, I have to be bureaucratic. Remember, we took the photo earlier. So there's, if you haven't gone and found yourself on the photo, we have it marked, and put your name by the number, okay? Probably by the end of today, there are about 5 or 6 people who haven't done that. We will make up names for those missing slots, okay? So it's out there.
Okay, so toward the end of last time, I was attempting to be very simple and hence clear, but I think I oversimplified to the extent that people got confused. So let me just start where we were at that point and clarify. So we started in higher dimensional string theory. We have all these quantum numbers. So the picture to have in mind is, if you want to consider a particular solution, you have a lot of choices to make. You have to choose the total dimensionality. You have to choose the internal space. So I had this picture. We're taking some higher dimensional space, and we're compactifying all but 4 dimensions on it. So this space, let's just call it big X. We have to choose X, and in there, there's some discrete choices, if you like, including the topology of the space and this geometry. Both are dynamical. And then there are these flux quantum numbers, which, as we've seen, are also, so flux quanta. And as we've seen, really, the Ramon ones become, if you like, these Qs, which are really have this Axion dependence inside of them, in effect. So, the details do matter. So at the end, people ask me some questions such as, don't the details matter? And indeed, they do for the specifics. But I'm trying to give you a big picture first, and I'll say a few more specific things as we go, as they come in. Of course, this is a huge subject, and I don't want to get totally bogged down in the moduli stabilization stuff, but we'll touch on essential features. So keep asking questions, but let me spell this out, hopefully a little more clearly as I started today. Are there any questions about the setup, though, before I get going? So have in mind some internal space X for this first schematic discussion. Have in mind some product space. So if you like a product of Riemann surfaces, meaning it could be either positively or negatively curved or flat, or a product of single scale compactifications as you wish. Okay, and the general pattern is, as I've written here, we transformed the Einstein frame. We have the dynamical string coupling. The leading term goes like G string squared. This is classical stuff. Well, all of this actually that I'll spell out is, but this is leading in the string coupling expansion. So it has this tree level potential energy that string theory comes with. It has the descendant of the extra dimensional components of the Einstein action, so integrated over the extra dimensions. And just as an example, if you think about this case of a product of Riemann surfaces, you're probably familiar with the fact that you know, just in terms of the scalings here, the fact that up to 2 pi's, you have, I guess, something like this, where H is a genus of the Riemann surface. So the way it scales is that, you know, in this single scale thing is R times L squared goes like 2H minus 2. So, you know, curvature is a 2 derivative thing. And that's why it ends up with 2 fewer powers of inverse length than the leading term there. So you can understand all these things in this kind of simple way. And the reason to focus on those dependences is, again, that, as you can see explicitly here, the whole thing goes to 0. So if you look at the potential projected in directions of weak coupling or large radius, you know, it goes to 0 either from above or below in both of these as you go toward the weak controlled limit. So it's important to keep track of those dependencies, and in order to get de Sitter or inflation, one needs competing terms of opposite signs at, you know, at subsequent orders in those expansions. Okay. Once we do that, once we fix, say, the overall size of the thing, the string coupling, there are other things like ratios of scales in a product manifold. You know, say if you take just a product of 2 Riemann surfaces of whatever genus, once you fix the overall size, there's the ratio of these sizes. And it's those ratios that actually have a much more elegant stabilization in terms of fluxes that I'll talk about. So, so there are sort of two types of these moduli, the ones that require this kind of 3-term stabilization at simplest, and then others like ratios of sizes of dual cycles inside the manifold, which turn out to have more like an x plus 1 over x potential. Basically, I can say it just physically. One can put flux on both of these, and, you know, the flux is quantized, so there's a certain, you know, number of flux quanta. The integration of the field strength over the cycle is some integer. And so the energy density there just blows up if you shrink the cycle too much. And so if you shrink this one too much and you have some flux on it, that, you know, causes a huge increase in potential energy, and similarly in the other one. And so you get this kind of x plus 1 over x potential for the ratio of the 2 sizes. Okay, so really, you know, it's kind of a mess. It's complicated to get everything taken care of in these string compactifications, but it is kind of this stupid at heart. Okay, so then let me continue with these terms. There's the flux terms. So the N3, again, is the notation for the magnetic flux of the H3, where H3 is d of the potential that corresponds to the fundamental string. And so this is integrated over the whole volume. So the volume of this space, maybe it's useful to spell that out, is L to the d minus 4, so that factor appears in various places here. And these scalings with L just come from, you know, this fact. So H3 L cubed is N, and starting from the energy of that magnetic field in the extra dimensions leads to this scaling with L upon dimensional reduction. Okay, so you can follow that through for all these things. For these defects, like these orientifolds and D-branes, it just matters what their tension is and how many directions they wrap. So that gives you powers of L correspondingly. The sign here is incredibly important, as I mentioned before, and that's basically because of the need for a dip in the potential. And so we talked about this flux term, and they're just similar ones for the Ramon fields. And again, they come with explicit Axion dependence in general. Okay, so this is the schematic version. I'll now talk a little bit about details that are interesting and come in, but let me mostly send you to the reviews of moduli stabilization and so on that exist to get a somewhat more systematic picture. So in fact, the last time I wrote up TASI notes, it was on that subject. So you can see more about this there, as well as in. I would recommend this recent book by Bauman and McAllister, which is about inflation but does more with the moduli stabilization and would have all the references. Okay, so let me maybe be a little more specific about. A bit slightly less schematic about the generalized fluxes, because those are important for Axion inflation, for example. So just to spell it out, for example, if you choose to work in 10-dimensional type 2B string theory, then these are specifically, you can find this all in Joe's book, but let me just write it down so that you can see a bit more about what really enters. And there are all sorts of duals of this that come in. Another thing that comes in that I might mention in the same level is, in addition, of course, to the potential terms, there are kinetic terms, and there are also Chern-Simons terms. So there are also Chern-Simons terms, such as one that enters in certain scenarios that's worth mentioning at this level is a coupling between the Ramon-Ramon 4-form potential and these 3-form fluxes. And you can see that, so this C4 is sourced. It's the Ramon-Ramon field that's sourced specifically by D3s and hence O3s and their anti-brane partners. But here you see in the action there's a term that specifically depends on that there's this coupling, and what that means is that when you what that means basically is that this combination of fluxes is another source of D3 charge. So this is an extra source of D3 charge. So in a 10-dimensional type 2 compactification, so now this is a 60 extra dimensions. A D3 brane that stretches all along the 4 dimensions and lives inside the space has to have its charge canceled by something, by Gauss's law. So one way that can happen is some combination of D3s, O3s, and this flux that altogether gives 0 net charge inside the space. Okay, so there's a bunch of stuff like that comes into specific examples. And I'll draw from that a bit more as we go. Are there any questions at this level? Let me do that. So when I shortly talk about, let me actually next spell this point out about the flux stabilization, having emphasized the 3-term structure already a few times, and then keep going. But again, ask me anything as we go. Are there any? Yeah.
So you think that the moduli stabilization is not something you can completely systematically?
For sure, yeah.
So which part is the least systematic? Which step is the?
Well, Leonardo gets to give these beautiful lectures where he's like, anything that can happen with a single scalar field, here it is. That's it, right? Part of the reason we can't do that, there are many reasons we can't do that in string theory, I suppose, but one of them is we have an indeterminate number of fields, first of all. So, there's all these possibilities. You know, just to characterize all possible, you know, compactifications and choices of these things and what the dynamics would be is, hopefully it's manifest how impossible it. Yeah. Oh, if you have a given one, okay. If you have a given one, you can do a lot. It's still complicated because there are many deformations of the metric that, you know, exist in the extra dimensions, and to be completely explicit, you'd have to really understand all of them, make sure there's no residual instabilities. And I think, you know, there's one example in 3 dimensions where all of that has been nailed down with I's dotted and T's crossed. Aside from that, there are very, very plausible mechanisms that have been suggested. There's you know, several ways in which one has identified very plausibly enough independent forces to fix all of the scalars. I'll talk a little bit more about those. I'm sort of getting there. But this, so just to maybe say a little more right now. You know, one thing, so clearly we need at least 3 terms in these directions. And so, you know, just staring at this, one way that could happen is you have a first term which goes like either the D minus 10 piece or negative curvature up here, or, you know, one of the other options from the top line. And then, you know, orientifolds here would have this nice feature that they give a negative term, and they give it at the first subleading order in G, and as is necessary. Or also I should say H3 flux over here on the first term. And then the third can be the Ramon fluxes. And again, these are generalized, so they have the axion dependence, but that can actually help stabilize during inflation. So every mechanism that I know involves this structure somewhere. Sometimes instead of these things, one includes certain quantum effects that are actually calculable and reasonably under control in low energy supersymmetric contexts. But okay, so, you know, in that context, there's a nice explicit example that's ADS, but I don't think anyone's claimed a very, you know, explicit example in de Sitter. There is just extremely plausible that it works. Yeah.
You pick and choose things.
Well,
But you're not exactly sure if it actually happens or something.
No. Well, okay. Once you fix a space and you start to lay out the ingredients that you want to, the stress energy sources that you want to use to do this job, it gets more clear why I'm saying it's so plausible. But I'm just being a little bit conservative and saying, yeah. I mean, what's the best way to say this?
Why are you still using the word plausible then?
Well, so for example, several, or at least a couple of the mechanisms involve something I alluded to here but didn't actually point to, which actually somebody else asked about yesterday, which is PQ brane. So these, you know, PQ7 branes come in, and you know, actually establishing where they all are inside some Calabi-Yau manifold or some product of Riemann surfaces has not been done, you know, explicitly. One can more easily work with certain limits that are essentially orientifolds and do things very, very concretely. But you know, you can see from the form of the potential, or in the Calabi-Yau case, the form of the superpotential, and so on, that you know, unless something surprising happens, there's enough independent forces in the game. I'm just saying that there's not a, you know, it's much more complicated than the Freund-Rubin solutions that give you ADS, where it's just some sphere with flux and that's it. You know, it's okay. and I think there are actually, I think there are several ways all of this could be simplified much more, which I could share with you maybe offline. So I think that's a real possibility. There's something called assisted inflation where you take. So one thing to say about this term is if you just erase everything else and you take this leading term, what does that give? So it's a scalar potential, and it gives the famous linear dilaton solution. So it causes the string coupling to roll down this potential at a certain rate, and it's in terms of so G is e to the dilaton phi, and phi is linear. So phi is something that's proportional to, I think, d minus 10 or square root of d minus 10 or something times time. And this is actually a well-known world sheet theory, actually, in string theory. So it rolls down in this way, but the thing I should say about it, though, is if you go to Einstein frame, in fact, it's even if you do flat slicing FRW, what this gives is a scale factor that, in terms of the usual FRW time, is growing like t, linearly in t, which is not accelerating, but it's almost accelerating, right? If you added any, if you take 1 plus, so it's on the verge of accelerating. And there's some easy field theory thing called assisted inflation, in which you can have a bunch of terms which individually don't inflate, but together they do. And this can fit into a framework like that. So one of my, when I get a chance, I'm always looking on the lookout for simpler ways to do this, partly because it's an interesting, simplifying this should help with the problem of understanding de Sitter entropy and that kind of thing. When it comes to applying this to cosmology, one probably doesn't want the most special choices. One wants a bigger picture, Okay, so and another thing somebody asked last time afterwards was, given this mess, how is it ever going to lead to predictions that can be useful for phenomenology? And I'll show you that as well. But the basic idea is just as it is in quantum field theory. So in quantum field theory, there are also lots of choices. You have to pick what theory it is you're talking about. You pick the content of the theory, and then you can, and its symmetries and so on, and then you can start making predictions. And my view of that in this context of string theory and cosmological predictions is very similar. It's just there's a simple argument that it requires an understanding of the quantum gravity corrections because of the fact that the Planck suppressed operators would change not only the predictions but the viability of inflation itself at order 1. And so given that argument, to be precise, one needs to do the model building within some theory of quantum gravity. But once you say that, it is just model building. It's like it is in quantum field theory. One can work in some regimes and find some mechanisms, and those in themselves can make predictions that are pretty robust, even though there's no claim that it's a general prediction of string theory per se. So it's just an upgrade of sort of field theory model building for the reason that it needs to be done with control of quantum gravity corrections. So that's the short answer, but we'll see sort of how that comes about in specific cases. Okay, so let me let me just come back to this flux stabilization thing again and incorporate the axions there. So I'll just again essentially say the same thing. So suppose you consider a space or a subspace that has the structure of a product of two spaces sigma, and you work at fixed volume for the whole thing. So let's say this one has a length scale L1, this one has a length scale L2. You can work at fixed volume we can even just make these, let me just, for this very simple case, make it a circle. Okay. So you can work at fixed volume, fixed L1, L2. And now if you put some leg of some flux on this one and on that one, so if you put some flux Q1 on this one, and you put some other flux, actually, sorry, if I want to, let me not make it a circle because I want to include this axion. So at fixed volume, L1 to the n, L2 to the n, so these are n-dimensional spaces. Okay, so put some kind of flux on L1, put some other kind on L2 that has this term depending directly on the axion. Okay. This could also happen if with a term that just depends on a flux, but I want to explain both how fluxes can stabilize these relative sizes and also how the axions can do that as well, and how that affects the potential for the axions, which is going to be interesting for inflation. So, okay, so here you have a simple setup, and by the same scaling, easily derivable scalings as before, this is going to give a contribution to the potential of the form. So let me just say L2 over L1 to the gamma from the flux energies. So this is just saying in equations what I said in words before, that the flux let me make this more intuitive notation. Okay, so this flux on this guy it costs a lot of potential energy to shrink it just because there's this magnetic flux energy density, and that goes in this direction here, but the flux on this one goes in the opposite direction. Okay, so it's again this x plus 1 over x type structure, two-term stabilization of this ratio L1 to L2. And furthermore, in general, in string theory, it depends not just on the fluxes themselves, but on the axions. Okay, and so in this situation, you can see you can solve for B here. So let's just call, so this is of the form y to the gamma q1 squared plus y to the minus gamma b squared q2 squared. So you can see that y to the 2 gamma will scale like b squared, or y to the gamma will scale like b. And so the potential goes like linearly with b. I've done this right for general gamma. And so rather than going like quadratically, like b squared, it goes like b. Okay, once you solve for the heavy mode. Okay, so this is an example of that flattening idea I mentioned earlier in the first lecture, where we saw that couplings to heavy modes will adjust, and this is just an example of it that's more faithful to the way that it works in simple string compactification. So, okay, so that we will be interested in. Okay. Now let me say that, since again, people seem interested in a little bit more of the formal details of such things, let me discuss that in a more sophisticated way, mathematically. So more generally, that kind of thing gives stabilization of the sizes of dual cycles, or the ratios of sizes of dual cycles inside more complicated manifolds. So let's consider, sort of in parallel, the complex moduli, the complex structure of Riemann surfaces, and also Calabi-Yau manifolds. So these are both very special choices of internal space. They have this nice feature of having metric deformations that separate into complex structure deformations, and in the Calabi-Yau case, scalar moduli. In the case of the Riemann surface, the overall size of the thing, and those deformations of the metric internally that can be described as complex structure deformations are stabilized in a nice way. That's kind of the generalization of that idea. So let's just depict this for a Riemann surface because it's easier to draw. But it's in the Calabi-Yau case, it just everything gets upgraded to. So here's a Riemann surface with all these 1 cycles. For a Calabi-Yau, it's a bunch of 3 cycles, and it's essentially the same idea. So there are A and B cycles on the manifold, and we can work with a basis of 1 forms. We'll be kind of interested in two kinds of basis of 1 forms in such a space in the Riemann surface case. The first one is those which are so-called integral, meaning that on, say, the A cycles, 1 forms alpha in this basis integrate to integers in this way, and similarly for the B cycles. And this is the basis in which the fluxes are expanded just as integers times these forms. Okay. But I'm saying that we're going to get from this a potential for these ratios of sizes for these complex moduli. And the way that works is as follows. Let's see. So you can, on a Riemann surface, there's another very natural basis of 1 forms, and we'll just transform between the 2 bases. So there's another basis of cohomology elements, I should have said, which are the so-called holomorphic ones. And these have the property that they integrate to, not to integers, but to this the complex structure moduli tau. For a Riemann surface, this is just the definition of tau. For a Riemann surface, this is more variables than you actually have. For a torus, this is the thing you might first learn about, at least, be more familiar with, just the complex modulus of the torus. Okay, so what you do then is take the easy expression in terms of the quantized fluxes and the integer basis, and transform to this basis. And when you do that and plug it into the action in 10 dimensions and reduce it. So I should say the other thing that's very useful about the holomorphic basis is that it satisfies this very useful property that its Hodge dual is minus I times itself, and that allows one to make this calculation very easily. So you do that. I mean, I'm quoting a few mathematical facts for you here, but I hope it's at least the gist of it is coming across. So you can do that, and you get a nice answer for the potential energy in terms of a vector of flux quantum numbers and some matrix that depends on the complex moduli. So I can write this out for you if one can write it out. Okay, so, and then once again, really these Q's should be generalized to the Q tildes that I keep talking about with the explicit Axion dependence. Okay, so that was an attempt to give you sort of the big picture, the scalings, and a little bit more of the kinds of details that come in. Are there any questions at this point? Yeah. Well, it's not really true that typically they've played some role. They play an essential role in the KKLT construction. They're in this quantum line. So let me actually, since you asked, I'll go to that. I'm happy to do things in whatever order. I could say this fairly simply. So there what you do is you, okay, I'll do a lightning review of that. So there you choose D equals 10, you choose R equals 0, because you choose a Ricci flat, a space which is classically a Calabi-Yau-Ricci flat. You work in type 2b, just for detailed reasons. And okay, if you do these things, you get a 4-dimensional n equals 1 supergravity theory, which has a potential which can be written in this way, plus d terms, which I'll just write as a word. And as always with supersymmetry, everything is coming in as a function of chiral superfields as far as the scalar stuff goes. Okay, so so the sort of pretty part of it is the part that actually Joe and Kachu and Giddings did with the complex moduli of the Calabi-Yau. So the Calabi-Yau has complex moduli, which is the direct analog of this Riemann surface thing I wrote up here, but where the 1 cycles become 3 cycles. So a Calabi-Yau has that basically that picture for its complex structure, and the fluxes, which particularly include a special role is played by the 3-form fluxes H3 and F3, because those are 3 cycles, do this job of stabilizing those degrees of freedom. Then there's the then there's the dilaton, and there's the there's the volume and all of the so-called scalar moduli, the sort of sizes of 2 and 4 cycles inside the space. Okay, so with the dilaton, it's actually, okay, there's a lot of details that come into this, but basically for the dilaton, it's a 3-term structure where it's H flux, F3 flux is the 3rd term, and the middle term is O3 planes inside the space, whose overall charge has to cancel by Gauss's law, and it does partly because of this H3 wedge F3 contribution to the flux to the charge of the 3-brane charge inside the space. So the dilaton is taken care of by this, and there's a level at which this is actually this by itself would be a supersymmetric minimum. Okay, so then what you really were asking about is the thing you were asking about, which is non-perturbative contributions to the superpotential, is what comes in when they want to stabilize the volume and the other 2 and 4 cycle volumes. Well, long story short, the superpotential contains, in addition to classical pieces, so there's a classical piece, I should say, W naught, which is a combination of F3 and H3. It's something like F3 plus tau H3 plus 1 over G plus C naught H3, I think. Which when you do the supersymmetric case, those fluxes that we understood component-wise over there combine into a kind of a combination which appears in the superpotential like this. So there's sort of a tree-level superpotential, and it being supersymmetric, before you include the scalar potential and supersymmetry breaking effects, you can ignore loops, and so this just is that plus non-perturbative, which include a contribution whose leading behavior is exponential in basically some 4-cycle volume. So rho here is the volume of a 4-cycle. So in my language over there, it scales like L to the 4th if we have a scale L. And again, well, for reasons that I haven't explained, but that have to do with the supersymmetry structure, the chiral superfield that appears here actually has terms that go beyond just L to the 4th, but this combination. So where this comes from, which will make this a little more clear, is a kind of instanton effect that you can think of as coming from Euclidean wrapped D3 branes, so-called ED3. And so the D3 brane action, the Euclidean D3 brane action, scales like the volume of the 4-cycle that is wrapped. And for relatives of the reasons I keep harping on with axions, it also depends on axions, and it does so in this way. Okay, so what that buys you, including the minus 3W squared, is a 3-term stabilization structure for rho and other 4-cycle volumes, which, as you say, involves. So far, this gives a. So far, this actually gives a 2-term ADS stabilization. However, there's a third ingredient, which will uplift it. So what happens? I should say again, at this level is a 2-term anti-de Sitter solution. But then they add the famous anti-D3 brane, which they put in a highly redshifted region, or so-called warped region. And that actually gives a power law contribution to the potential as a function of rho, which is analogous to the ones I wrote up here for these, in my general characterization. So it's a term like this, which is a power law in this row. And so because even though it's a power law and hence would seem to be huge compared to this exponential, it's okay because it's in a highly redshifted region. Okay. So it long story short, yes, you're right. There's a nice class of examples where quantum effects are essential. It's again a 3-term structure, but just with different ingredients. Yeah.
Sorry, just to understand the G-string plot.
Yes.
So, as you said, there are several order G-strings that compete, right?
Different orders in G-string that compete. Right.
So, what is the fact that makes ultimately X3 square weakness? Like a number of blocks?
Oh, it's because they are at different orders. So it's just it's a really interesting and important but I'm sort of just presenting it as a fact about string theory that these Ramon flux terms, just originally in the higher dimensional action, these generalized flux terms came with a power, extra powers of G.
Why that term doesn't have a G-string over the 1?
Okay. No. Excellent. I now I know what you're asking. Yes, exactly. So one. Yes, I'm glad you asked. I should spell that out too. So, what Leonardo is saying is, we're making different orders compete. There better be some compensating hierarchy in the coefficients in the expansion, and that is true. So let's I think I even have the number, so I'm going back. Okay, so if you just write a potential which is this stupid thing, I'm using tilde to not confuse the notation of these coefficients with the axions, but yeah, so we have this, and so, okay, so you get a de Sitter minimum only if you live in a certain window of these coefficients. Otherwise, you can just lose it, or you can drop below 0. So, this is the thing that quantifies what the conditions on these things have to be. And indeed, in all of the scenarios of interest, or that have been worked out, one of the things that, when I say it's very plausible, one of the things that's been accomplished, aside from just showing there are these independent terms, is showing that one can get the various ratios that are needed for this dip. So the way it works both in this Calabi-Yau case and the product of Riemann surfaces that gives just a perturbative stabilization in a fairly similar way is just another neat fact about string theory, which again was introduced and employed in the paper by Joy et al. Actually, which is, so I'll just give you an idea of how, for example, the negative term can be strong enough, which really needs to be here. Yeah, that's exactly the. The way that can happen is, okay, so I said O3 over there, up there. This is actually getting into details that kind of go beyond what I've explained, but let me just, it's absolutely an important point in these constructions, so let me indeed say more. So there I just sketched, okay, O3s give a negative term, but one neat thing about in more detail about these spaces is that there are so one of the elements of the construction I didn't describe explicitly is these PQ7 branes, which the string theorists would have heard about. So what this construction really is an F-theory construction, or one which includes PQ7 branes. And what these are, it's essentially like a contribution to curvature from a varying axion and dilaton that varies around a defect and produces an object that scales like curvature. Okay, so you have those, but you have them in a way such that in the whole extra six dimensions, they triply intersect. Okay, so you have PQ7 branes and you have their triple intersections. And these give, at the point of the triple intersection, they introduce extra O3 charge and tension. If I went more into the details of these orientifolds, that becomes clear in a certain limit where they're obtained by a projection. But what happens is basically that the effective number of O3s scales like the number of 7 branes cubed. So that is a nice way to get a large number of negative contributions into the game. So yeah, another aspect of it is that this W naught is tuned to be small so that it can compete against the exponential in the other direction. So yes. So it's that kind of thing that's done when I say the mechanisms are very plausible. It's but when I say it's not all just explicit, it's because that's basically not humanly possible with these complicated spaces. So okay, so how are we doing on time? Okay, so. Well, since this is a formal school, I want to sort of open a parentheses and make a comment about how this structure fits in really nicely with the sitter holography. So what I'm going to say is really very simply based on the need for this 3-term structure. So one of the great things about this general subject of cosmology is that there are so many interesting open, conceptual and more formal questions, such as how does one generalize the ADS-CFT correspondence to the case of interest in the real world, and also the case that's, again, much more generic in string theory than the ADS or Minkowski space. So what I'm going to say next is to show that the need for this 3-term structure fits very well with the upgrade of ADS-CFT to de Sitter space, and this is something that I can explain given what we've already done. So let's take some ADS times S sort of space. So it could be ADS5 times S5 or ADS3 times S3 times, in that case, times T4. There are various versions of ADS-CFT. And first, let me just work. So let's say the ADS is in D dimensions. And let me write down, in the same way that we've been describing it here, the potential energy in D dimensions. By write down, I mean I'll just explain how it works at the same level as over there. So you're probably used to the derivation of the Freund-Rubin solutions just using the 10-dimensional equations of motion. There's a good description that we can get using this dimensionally reduced effective potential, which gives, of course, the same results. And in the language we've been using, it's a playoff. It's a 2-term stabilization to a negative cosmological constant, where the internal space is now positively curved, a sphere or a orbifold of a sphere or a more complicated. So Xn is a sphere, or fancier positively curved internal spaces. And the thing that stabilizes it, that turns it around, is not in the horizon. It's Ramon flux. Okay, you're probably familiar with this in some language. And if you put in, for these various cases, those scalings, you find the familiar answers for okay, let me say, for example, let me label this axis as roughly speaking, 1 over the size of the sphere, but there's the dilaton, and one stabilizes that or gets a flat direction depending on the example. This is the basic mechanism. So I want to connect that to, before discussing what happens to, so I'm going to be interested in what happens to this when we add ingredients that upgrade it to DS instead of ADS. Okay, but let me just review first the rest of the essentials of ADS CFT that we'll want to use. So this is the d-dimensional effective potential description. The argument that Juan originally made for ADS CFT was, and in these generalizations, involves a stack of D-branes which are at the tip of a cone over X. R6 and the ADS 5 times S5 case is a sort of extreme example of that. More generally, it's a cone over these spaces. And then one takes the near horizon region and gets the duality. But let me back up for a moment and work with the brane construction and belabor the geometry of the cone, because what happens to that will be extremely interesting in the upgrade to de Sitter. So what is the cone? Well, the cone, since for these lectures this morning we are cosmologists, we will realize the cone, which has a metric like this. We will think of it as the solution of the Friedmann equation in the radial direction, which it is. Okay, so one can think about the Einstein equations, as you can just like you can get the Friedmann equation, you can get a radial evolution equation for A of R in this metric, and if you are careful about how the signs work, this is the equation, and so it gives A equals R. Okay, so there's the. Okay, so there's that, and then there's also the near horizon metric. Oh, and the other thing to say about the cone is, it's what you get. So let me spell this out as well. It's clearly what you get in this Friedmann equation from simply the curvature of X. So again, it's very much like time evolution, having postulated a curvature of the homogeneous spatial slice. Radial evolution, having postulated this positive curvature, gives A prime over A squared equals plus 1 over A squared. Okay, so it's driven by that, but the cone itself does not contain the flux. So the D-brane source some flux, which in this stabilization, is the term that is positive, but the cone itself is the solution without the flux, because it's the thing that the branes sit on. Okay, so all these things we'll be interested in. What happens to them if you add ingredients to uplift to de Sitter in the simple way we've seen that you need to do, or I should say the minimal way we've seen that you have to do. String theory. Okay. before I do that, let me just record the near horizon metric in a certain slicing because it will be useful. So we all know how to write the ADS metric in various ways. I'll write it here in a de Sitter slicing, which is as good as any for ADS CFT. And that here's the metric. So it has the features that you're used to. It's just de Sitter sliced now. And in particular, as usual, the warp factor goes off to infinity as you take the radial coordinate off to infinity. Okay. Okay. So what I'm going to do next is just show, just based on the need for this three-term structure, which, by the way, is one of the many ways in which not anything goes in the landscape of string theory. It's not true that there's no structure and anything goes. This is a clear example of that. So we want to see what happens to ADS CFT when we add what we need minimally to upgrade it, uplift it. Okay, so and we'll see something really, really nice happens. Okay, so I just take a very lowbrow approach to this problem. Let's just ask what happens, as I keep saying, ask what happens if we, add ingredients, are really just the essential that we've seen we always will need to do to upgrade ADS to DS. What happens to all these elements of the ADS CFT duality? Okay, so first, let me actually label these things. I'll just call this 1 and this 2 and this 3. Okay, so first of all, just at the level of the geometry, the macroscopic geometry of de Sitter with a de Sitter slicing parallel to the one that I wrote for ADS is the same, except it's a sine, not a sinh. So this is actually even more intuitive than that one. Well, depending, I guess, for string theorists, everything ADS is the most intuitive. But de Sitter, Euclidean de Sitter is just a sphere, and all this is the slicing of the sphere, and in this way, the foliation of the d-dimensional sphere with d-1 dimensional spheres. And those spheres become this de Sitter in d-1 dimensions. Okay, so this is that metric. And what you see here is that whereas in ADS there's the infrared, where the warp factor, the gravitational redshift factor, G0 goes to 0, there's one place where that happens. Here there's two places. So the infrared is at W equals 0 and pi. What this is it's a foliation of the de Sitter static patch, an observer patch of de Sitter a foliation of those by d-1 dimensional de Sitter spaces. Okay, so this is just a simple geometric fact. So that's what happens macroscopically. And what happens a little more microscopically because of the uplift will be something parallel to that. The other thing I should note about this is that there are two IRs, and also there's a finite UV. Okay, so we'll get there as well. So what happens to the potential? Well, that's what we've been talking about in considering moduli stabilization. If we start with such an ADS minimum to get de Sitter minimally, we better add something that overcomes the leading negative term of the potential over there to give a leading positive term, and then we better add an intermediate negative term, the thing we've been getting from orientifolds and their fancy generalizations from 7-branes and whatnot. Okay, so, well, the simplest way you can think to do that, well, again, we've sketched this before. You can have d bigger than 10. You could have, depending on the details, you could have a brane wrapping the whole thing. You could have, r less than 0 instead of greater than 0. And then in here, you need something like O-planes, and the third term can just be the same. So that's we've talked about. And now I just want to say what that implies for this brane construction. So before we had this radial Friedmann equation, which gave us the cone. So what happens to that? So what that happens to that is very nice and simple. It's the first term has flipped sign, and depending on the details, it'll be some power of a over there, but it'll be negative instead of positive. And because of the need for the intermediate negative term, say from orientifolds, one gets in this Friedmann equation a second term of opposite sign, and also a power that is bigger as a function of 1 over a than the first term. That's just a direct result of this 3-term structure in the uplift. So what does that give for the radial evolution? So here the radial evolution gave us the cone, and again that's the right solution for the thing that the branes probe in the brane construction. That is the solution without the flux corresponding to the branes, but with the geometry and everything else. So anyone want to? So if you do a free, this is like a closed universe. Okay, it's like so the solution of this radial evolution equation is it starts at a point, it grows to a finite maximum, and it shrinks again to a point. So it's the same as the Friedmann equation for a closed universe in time, which is that. So automatically, we've gotten the same structure that we had macroscopically. You now need to put the branes, and in this case, because this is a compact space now, by Gauss's law, you need to include their conjugates. You need to put those in, and the resulting solution has 2 low energy sectors, and again, it goes up to a finite value, so that also matches this macroscopic description. So the upshot is that you can derive a so-called semi-holographic uplift of ADS-EFT to de Sitter space, which has 2 low energy field theory sectors that are cut off at a finite scale and coupled to the lower dimensional gravity. So one hasn't fully decoupled all of gravity, but one has removed the higher dimensional gravity and in favor of some matter sectors. And it's a direct consequence of, so you can see this had nothing to do with string theory. This is just the way that the metric works in de Sitter space. What string theory has added here is the Dine-Seiberg problem, that the minimal way to do this de Sitter type of solution is through a 3-term structure of this kind. And then that had the automatic consequence that the brane construction requires the two sectors that were predicted by the macroscopic geometry. So I think not only is it just a technical fact that we have this, this runaway behavior, but it's happening for a reason, and for a very good reason. Now, you may have heard more of the so-called DS-CFT correspondence. Let me actually show you a fun coincidence between the two. So they're conceptually quite different in that the DS-CFT requires features that really don't seem to agree with these runaways in string theory and so on. It involves trying to take seriously the far future boundary of de Sitter space as the analog of the place where the field theory lives in ADS-CFT. But actually, if you do that, so let's discuss the bare bones of that proposal regardless, and we'll see another amusing coincidence. So this DS-CFT is a conjectured dictionary between, again, a theory which ultimately has dynamical gravity, but the wave function of this gravity theory on de Sitter space is conjectured to be calculated by the partition function of a CFT. And this wave function is a functional of the sources of the CFT. So the sources include the metric, the three-dimensional metric, or the d-minus one-dimensional metric on this slice. So this is ultimately dynamical. And so in particular, if you take this as given and you want to compute all the observables that you might want that exist in the theory, those would include, expectation values of operators, which, given this wave function, require you to well, they're given by this kind of expression, right? If I give you the wave function, this is how you compute the expectation value. And so let me just specialize the source to the particular case of the three-dimensional metric on which all of this depends. And you see that what this is a calculation that, first of all, has dynamical gravity. So that is, we have to understand how to integrate over metrics. So just like what I showed over there, this has dynamical d-1 gravity. But also, this is like the partition function of a system with two Matter sectors, which are coupled to gravity. So these wave function factors, psi dagger and psi here, have effectively are giving you a calculation like you would have in a field theory with two Matter sectors. So there's a coincidence here that this thing that is really derived from uplifting de Sitter, anti-de Sitter to de Sitter, which gives you a limited version of holography, but a correct one, where there's clearly two low energy Matter sectors and still d-1 dimensional gravity, with a lot of symmetry in the problem, gives a framework which is conceptually quite different from this one, where one tries to make sense of these slices which no single observer can see and so on, and which don't account for the decays. But it's interesting that the resulting calculation has the same basic ingredients. Yeah.
In this implementation, you end up having the central charge of the CFT is like negative.
Yes, but you know, things like that are okay because this is a Euclidean CFT.
But you find that here.
No, here everything is just much more prosaic. It's time is time. It's the you know the one starts with actually the three-dimensional example I alluded to before of a de Sitter construction was done as an uplift of the ADS3 times S3 CFT2 dual pair. And so you start with some specific ADS CFT, say the one that has matter sectors that involve the degrees of freedom on 1 branes and 5 branes, and you add stuff to get this. And so the matter that there is still basically that of the 1-5 system plus the deformations of it that are introduced by these ingredients. And so it's really much more similar to ADS CFT in that sense.
So you're just putting out the coincidence of just there being 2 here and there being 2 there.
Yeah, exactly.
This is a wave function.
Exactly. So conceptually, that's different. The way things are organized is different. The issues are different, but they both have the feature that, just in terms of the computations, there's 2 matter sectors that are cut off, that are coupled to gravity, dynamic gravity. I doubt that's an accident, and I seriously doubt that this effect is an accident as well. So I think that these technical things that we deal with when we consider moduli stabilization and inflation and so on are happening, you know, for a reason. Another reason may be the much discussed interpretation of the cosmological constant observation that I mentioned in terms of the the possibility that it's a selection effect, the anthropic explanation, which requires a different aspect of this, which is its many choices, all these flux quantum numbers and D and topology and so on, plausibly give enough structure to allow for an interpretation of the tiny observed value of the cosmological constant as a selection effect. So we, most solutions don't have that property, but there's a dynamical scanning among them and enough different possibilities that we can understand what we see as a selection effect, in the sense that we would only observe it if the universe is, even though it's a very special case, if the universe is big enough and so on. So, the string landscape has this mess for, possibly very good reasons, both phenomenological and, here I'm arguing, also conceptually. And next time we'll finally get to how, having understood this, we can identify rather robust mechanisms for inflation with very interesting predictions. And we'll see how much of that we can cover, but that will be, I think I'm out of time for today. So are there any other? Yeah. Well, let me just talk about it in both ways of organizing the problem. In ADS CFT, or let's back up just in black hole physics. So in black holes, in string theory, there was a computation of the microstate count of entropy, and it was highly relied on supersymmetry, and that hasn't been generalized to Schwarzschild black holes, and it hasn't. And it's for similar reasons. It's difficult to generalize to de Sitter space, but that's understandable. It's just the fact that once you have a more generic situation with less symmetry, it's not as easy to extrapolate from weak coupling to strong coupling, which is what they did in that nice entropy count. So ADS-CFT was kind of an outgrowth of essentially that entropy count and just the physics of the branes. ADS-CFT, of course, goes way beyond supersymmetry. It's wonderful that way. But that's one of the ways in which, its origins are, it's clear that, its origins are more mathematically precise than they probably can be here. And I think the other thing is the fact that gravity really doesn't decouple. I mean, it's just a mistake to dismiss the whole thing because of that. Since in either case, since part of the problem has been given a holographic description. So one has gone from d-dimensional gravity to lower dimensional gravity plus a bunch of matter, which is clearly a concrete step toward a complete description. But I think it's just because of the finiteness of de Sitter, it's just always going to fluctuate. ADS has this boundary which pins things down, and that's nice enough for the duality, but it's highly unrealistic. And that whereas here I think, okay, it's just a true fact that things fluctuate, and we're not going to get out of that within the de Sitter phase. I can say one more thing though, since it's a great question about here I wrote, I emphasized the role of the metastability of the potential, but then I just talked about de Sitter as if it went on forever, and there is a decay that's non-perturbatively slow because of the metastability. So the real picture we have of de Sitter space in string theory involves, if I draw the Penrose diagram, these horrible pictures of many exit regions. Okay, so basically each observer will eventually exit from inflation and de Sitter due to this runaway. So that can be incorporated very easily here. And in fact, what happens when you do that, for reasons I'd be happy to describe to you either now or offline, is that the persistent d-1 dimensional gravity that I mentioned here becomes more and more weakly coupled. So as you decay and evolve down this unstable region, the one way to say it is just the d-1 dimensional Newton constant or Planck mass is time dependent. It goes off to infinity compared to the scales you're interested in. So and also the Busso entropy bound goes off to infinity. So you accrete another aspect of ADS-CFT is the field theory has an infinite number of degrees of freedom, so it can formulate this whole space very precisely. That also happens as you take this decay into account. So it becomes precise in the far future. Things get better with time. I'm an optimist. But so this, I really think this. So I really think it's silly to expect the same level of precision here as you would. This is not what you were saying, but just to elaborate a bit more. It's just silly to expect the same level of precision here as you would have in some highly supersymmetric situation. But that doesn't, it's not all or nothing. That doesn't mean you can't say anything. And in fact, this kind of concrete, but admittedly somewhat qualitative, but still concrete, result, this kind of thing, there's more things like this there and here, are on the table and quite possible to work with. So it's funny, a lot of, pretty much every inflationary mechanism that I have happened upon personally in my research has been the direct result of trying to simplify that to address this problem. DBI inflation came from thinking about branes approaching the infrared here, and how did that work in the field theory? And, oh, wait a minute, it's just going arbitrarily slowly. So then obviously you do inflation with that instead of this crap, right? And then, actually Axion monodromy came from another mechanism for stabilization that made that structure pop out at us. So it's kind of interesting just how the two subjects that I'm trying to cover here, the general subject has these different sides. It really has these, super interesting but challenging conceptual questions. My own view of it is we'll get more and more close to answering these the better we develop the technology. So ADS-CFT came sort of serendipitously as well from people dorking around with brains and bouncing things off brains and whatnot. And I just think the structure of the string compactifications, we've already seen it, and just both formally and phenomenologically, but I think it'll just continue to guide us more toward solutions to these problems, as opposed to trying to guess them from here. That's at least my philosophy. But anyway, to me, in my mind, the conceptual stuff and the phenomenological stuff that I'm going to come back to and focus on for the rest of the lecture is pretty connected. So, any other questions? Okay.